You can watch the first 10 minutes of the earlier recording. So do this, and then you can put in a return if you want, or just put in a curly bracket and it'll return automatically.
That's a stupid question.
Yeah.
So what does that one line under the main function do? The struct node?
The struct node?
Yeah.
So that's a variable declaration, okay? If I had said integer list bracket 100, that would make an array of 100 integers called list. Okay, here it's making an array of 100 struct nodes called list.
I see.
And all it's doing is allocating memory. It's not actually giving values to these things. It's finding a spot where it can store, in this case, 300 integers in a row. And it's reserving it and saying, when I say list, I mean the beginning of that array.
Do the names have to match up for the node, or I mean the structure?
So, match up where and where?
If we're calling it node in the list 100 part, and then in the actual init statement, if we're calling the structure node, do they have to be the same name?
So it has to be struct node, right? Node is actually the type of the variable.
Oh.
Okay. But, right, I can call my array list in here, and I can call it X in here. That's perfectly fine.
Could you change the name of the structure to
Like struct node 2 or something.
Yeah.
It would be a totally different structure, and it would have nothing to do with this.
But would you have to change it in the void main function if you're trying to change the thing, or is it gonna just understand it when you're calling it from it?
So one thing you could do, and I don't know if this addresses your question or not, if I have another file, I could make a struct haha with these fields, and my init function could take a struct haha, right? And that's going to turn out to work fine. Because the only thing a struct is really is a particular organization of these fields in memory. Right? When I say struct node, it's going to say, okay, the first 4 bytes are data, the next 4 bytes are next, the next 4 bytes are valid. And in that sense, the actual name of the structure doesn't matter. But in any case I've ever seen, you want to, if you're talking about a struct node, you want to make sure you're calling it a struct node everywhere. Yeah?
So in the test bed, how would you check to make sure that the function is doing what you intend?
Excellent question. So this is the thing you're writing, and you're going to assess. But if you want to test it ahead of time, write your main program, declare your struct node, call init. Okay, how do we know that it's doing the right thing? Make some print statements. Print out list bracket 0 dot valid, list bracket 0 dot data, list bracket 0 dot next, and just look at the output and make sure it says 142 negative 1. And then make a for loop from 1 to 99 and print out list bracket, I don't know, %d equals valid, next, and data. Print those out, and you should see these 3 numbers printed out 99 times, and it'll be really obvious if something didn't get initialized the right way.
Isn't that what your temporary main does?
That's basically what it does, but I think it does something different too. I don't know how convoluted I made it. Okay. So later the ODPs get more kind of convoluted so that it's not easy to sort of fake it, and you have to do your own test bed. But the first ones are more straightforward. Yeah?
Can we create or define a structure inside the main function, or does that?
Mm-hmm. Yeah, so I would actually define this inside, at the top of your file outside of a function. You could define it inside main, right? But then you have to also define it inside init and any other function. So it's usually cleanest if you just put it in the very beginning of the file. And eventually, pretty soon actually, we're going to switch to actually putting this in a .h file and just saying number sign include. So that if we have 5 files, we don't have to make sure we type it in the right way every time. Or if we want to change it, we don't have to change it 5 different places. We just change it in the .h file. So this will feed into the whole modularization idea that we'll be talking about a lot. All right, so ODP, everybody think they can make a good stab at that? Again, this is one of these things where if you understand it and you sit down and write it, it's going to take you 5 minutes. And you'll compile it up, you'll assess, and it'll say 10 out of 10, and you're done. Okay? But if there's something that wasn't quite, completely understood when you learn it. If there's something about structures that you don't quite understand, if you forget that there's got to be a semicolon here, right? This can take a long time. You can spend a lot of time hunting down details, and there's a lot of rabbit holes out there, right? If you hop onto Stack Overflow, that's oftentimes a big rabbit hole. And you should not need anything terribly sophisticated. It's really this plus one more for loop down here. So if you're looking online for ideas and you start finding mallocs and frees and mem sets and all this kind of stuff, you're going down a rabbit hole. Okay, come back and just think about this stuff. Okay, but again, it's time well spent, because if there's something about arrays or passing arrays to functions or structures that you're not quite 100% crystal clear on, this is the time to figure it out, okay, between now and 8 o'clock tomorrow morning. So that tomorrow in class, when we start talking about PA1 and we're passing structures as arrays to functions and stuff, we're all clear on what that means and what the mechanics are, and we can start building on top of that. So hopefully the ODPs don't end up taking a lot of time, but if they do, that's okay, right? It's time that has to be spent.
So when I'm trying to compile this, I put in the same thing that you put there. It's telling me that the parameter, an error parameter name omitted.
Okay, so when you write your function init, you have to actually name the variable that you're going to pass to it. And if in the actual declaration you just do this, right, I think that's what will give that error. So remember, this is a function prototype. This is telling the compiler, when I get around to calling init, I'm going to pass it a struct node star. But when you actually write the function, you define the argument to be struct node star. You also put the name of the variable that you want to use. And there's no semicolon after that parenthesis. Does that apply at all to?
Yeah.
Okay.
I just added the name and I got another error.
And make sure you get rid of the semicolon.
The semicolon after the struct node?
After the parenthesis.
Yeah, I don't have
Okay.
but it's saying there should be a semicolon or something before that now.
So that might be a previous statement, but I can look at it right after class ends if you want. All right, so yeah, when you're testing this on your own, right, GCC-O, whatever you want your executable to be called, the name of your, if your main program is included in init.c, just init.c. When you're ready to assess, compile with this line down here. It says compile init.c, that's the code you just wrote. Link it with main202.0, that's my test bed that I provided to you. Call the output program main202. That's what that GCC statement says. And then run the assess command. Main202 is the executable, and init.c is your source code. Use the G command, it should give you 10 out of 10.
Silly question.
Yeah.
What does that actually do, that GCC part? Not actually GCC, but like just, what is it accessing right there? /temp/main202.
So I wrote a main202.c, okay, which uses your init function, does something similar to this, and then some print statements in a loop and so on. So I made a main202.c. I compiled it by saying -c. So GCC-c main202.c, which doesn't give me an executable program, it gives me what we call an object module. That's what main202.0 is. So it's a compiled version of my test code. And then that links in with your init.c. It's basically the main program that links in with your init function and creates an executable program. And that's also something we'll be digging into a lot, because we're going to be modularizing our code. So you're going to make a main function for PA1, you're going to make a set of linked list functions for PA1, you're going to link them together like this using a makefile. So this is all preamble to stuff you're going to be doing basically throughout the quarter. So we'll get lots of exposure to it in different forms. All right, so what I want to do next is have you break into groups. So we got about 22 people, so there's enough space for 5 at least groups, possibly 6. So let's say 4, maybe 5 people to a group. find some people to work with, find a spot on the board. There should be erasers and markers scattered throughout. And let's do some linked list operations like we were doing yesterday. And so I want you to start off by just making an array of these struct nodes. So just this part of the table, and you don't have to do 12 entries. We can probably just do like 6 or 7 rows. But a field called data, next, and valid, and also list what the index of each entry is. So just replicate that piece of the table on the board big enough that you have space to write in these boxes and make changes and so on. And then we'll go through actually doing some operations.
It's actually over.
How many has to be in there?
Yeah, probably 6 is plenty.
Nick, so like, could you use like a two-dimensional array, do you think?
In some sense we are.
Yeah.
But yeah, you could do a
But I
two-dimensional
guess
array.
you can't
and-
really name it either, so it'd be kind of confusing.
You could define data to be 0, valid to be 1, next to be 2, and then use those as indexes. That would work too.
So is there a way for you to like iterate your structure, like for each property?
If you had a two-dimensional array, you could. But no, not really, but there are ways you can do it. But
Yeah, couldn't you set properties equal to like 1, 2, 3 instead of data next value,
Mhm.
and then have a loop inside a loop?
Right. All right, so we've got an empty structure up here. All right, so ODP 202 has you do a bunch of initialization, okay? It's a bit of overkill, but I want to make sure that you can touch all the different fields at all the different entries. But in reality, to initialize a linked list to be totally empty, we only really need to do like 2 things to our array. So any idea what things we need to do to initialize this to represent an empty linked list?
Make index 0 valid.
Make index 0 valid, right? Index 0 is going to be our sentinel node. So remember, we're going to do sentinel nodes for the first 2 assignments. So we can set index 0 to be valid. What else do we have to do with that sentinel node?
Next to be some sort of invalid.
We need to set next to be something that represents the fact that there is nothing after the sentinel node. It should represent the end of the list. So for now, we're just using the value -1. Eventually, we're going to use a value called null, but we'll just set that equal to -1. Do we care about the data field in the sentinel node? We don't. Okay, we're never going to use that. Sometimes it's useful to put a peculiar value in there, though, so that if we accidentally bump into that data value, we'll recognize it. So we might set that to 42 or 999 or some value, so that if we're looking at our linked list and we suddenly see this number 42 that keeps popping up, we'll say, I must be looking at my sentinel node, right? But really, the only thing we really need is the next field should be equal to -1. Okay, so we initialize a sentinel node. There's one other thing we need to do to really make this an empty list. And
Set
so
everything else to 0 in the valid.
set everything else to 0 in the valid field. Okay, because the valid field is how we're going to know that this box is effectively empty. And on paper, we can just look at it and see it's empty, but computer, there's always stuff in there. So we're going to go through, we're going to set all these valid bits to 0. Right? And this is the essence of what ODP 202 does. Different values and some extra things it's doing, but basically, we set up a sentinel node a certain way, and then we set the valid fields everywhere else a certain way. Okay, congratulations, you have an empty linked list. Okay, perfectly valid linked list that contains no data. Okay, and that's not a small thing. If you don't initialize this and start with an empty linked list the right way, trying to insert into it will probably segfault. Okay, so this is an empty list, but it's really, really valuable. So let's do some operations. Let's insert the number 30 into this list. So what do we do to insert a 30?
Find an invalid index.
Find an invalid index. Okay, what's the first invalid index? Index 1. Okay, so we found index 1, that's available. What should we do with index 1? Okay, mark it as valid. And then
Set the data to 30.
set the data to 30. Okay, good.
So next to your sentinel node should be 1.
And the sentinel node should point to that. So change the sentinel node's next to be a 1.
And then the actual one would be, well, -1.
And then set the new node 30's next field to be -1 to say that's the end of the list. So everybody good with that? Okay, let's insert a 40. And let me write down these steps this time. So let's insert n. So what's the first step?
I mean, if you want to get a little creative, you could just make like 10.
So find an invalid entry. So that's entry 2, right? Okay, what comes next? Set valid equal to 1. So that becomes a 1.
What, change the data to the number?
Set the data equal to n. So we're inserting a 40, so this becomes a 40.
Set node dot next, node bracket, set the next value to -1.
Okay, set the next value equal to -1, because there's nothing coming after the 40.
And then for the one before, you set it to 2.
And then set the prior nodes next equal to, in this case, 2. All right, so what does our list consist of right now? Well, node 0 is a sentinel that points to node 1, which has a 30, so the first thing in our list is a 30. That points to index 2, which has a 40. That's the second node in our list. And that has a next value of -1. That's the end of the list. So right now, our list looks like this. All right, it's got 2 pieces of data, 30 and 40. All right, everybody good so far? So let's write some pseudocode on this next one, which is going to be a little trickier, because our next operation is insert 35. So I'm going to write down some pseudocode, some high-level steps that we can perform systematically to do this insertion. So the first step we've been doing is to find the next place that we can use in here, find an entry where valid is equal to 0. Okay, so I'm going to call that location current, and I'm going to say current equals index of first entry with valid equal to 0. And in this case, that's index 3, so I'm going to put a comment here which says current equals 3. Okay, and then we want to set that node's valid flag to be 1. So assuming I'm still calling this array list, I'm going to say list bracket current dot valid equals 1. And magically, this can change to a 1. Okay, what would be some pseudocode for setting the data value equal to n?
List current dot data equals n.
Perfect. List bracket current, that's this new index we're using. Dot data means the data field, set that equal to n. So our operation here, remember, is insert n, where in this case n is 35. So we set a 35 here. All right, now we're inserting in between two nodes here, so we don't want to set 35's next to be -1. We want it to be something else. And we're going to have to change the previous node to point to our 35. So before we can do any of that, we need to know what the node is immediately prior to this new node we're inserting. So I'm just going to give that a variable name. I'm going to call it previous. I'm going to say previous equals index of node after which we're inserting. And we need to talk about how to find that, but we're smart humanoids, so we can just look at the picture and figure out we're putting in a 35, that's got to come after the 30, and the 30 is at index 1. Okay, so I'll put a comment here, previous equals 1. So knowing that our current node is at index 3 and our previous node is at index 2, what changes do I want to make now? What do I want my current nodes next to be equal to? 2. Now how do we know it's a 2?
That's the next largest after it.
How else could we tell that?
The next
Because
value
that's what
is-
the previous one is.
Because that's what the previous one was pointing to. Right, so the effect is we're inserting a 35. If we know the previous node, whatever that previous node is pointing to, that's what 35 should point to. Right? The previous node was a 30, that's index 1. That's pointing to 2. That's where we want our new node to point. So we can write some pseudocode for that, which says list bracket current dot next equals list previous dot next.
And then you're gonna have to set the previous next.
Right. All right, so look at the previous node's next field, make our current node point there. And then, yes, we need to take the previous node, and instead of pointing where it was pointing, we want the previous node to point to our new node. So one more line of pseudocode, list bracket previous dot next. And what should that be equal to? That's just equal to current, because current is the index of our new node. So we just set that equal to current. Current is equal to 3, previous is equal to 1, so this down here changes to a 3. So what's our list? Start at the sentinel, that points to a 1. We started with a 30. That points to a 3, which is 35. That points to 2, which is a 40, and that's the end of the list. So what we've actually done was we made a new node with a 35. We changed the previous node to point to the 35, and we changed the 35 to point where that previous node was pointing, which was a 40. Now this is turning into a spaghetti ball, right? That's okay. Our array is not ordered anymore. There's the first one, there's the third one, there's the second one. That's okay. We're never going to just start at the beginning of our array and say, hey, our data is a 30 and a 40 and a 35. We're always going to follow the links. And when we implement this in dynamic memory, it's going to go all over the place. And we're not going to have any idea where this stuff is stored. But we're never just going to go through memory and look for our data. We're always going to start with the sentinel node and just follow the links. And that's guaranteed to take us through our data in the correct order. And when our link says, hey, there's nothing after me, we know we're at the end of the list. Okay, so at this point, I'm going to copy my data down here so that it's not as difficult to read. And I'm going to send you home with some worksheets and some inserts and deletes to perform. I'm going to have you do this as an ungraded homework and bring it back tomorrow. And there's 4 of these tables on here. I'm going to have you do 8 operations. So you can do basically 2 operations on a table and then copy it down and continue on the next one. So it'll be easy for me to look at what you've done and verify that you understand it or identify where a misunderstanding might be. So let's do one more insertion operation. Let's insert a 10. And this is tricky because now we're inserting in the beginning of the list. So we're inserting a 10, right? Our first node is a 30. And we're trying to insert something before that. But it turns out we can do exactly the same algorithm we just did. It's going to work perfectly fine. So what is current going to be equal to? What's the index of the first entry with valid equal to 0? 4. And n is going to be equal to 10. So list bracket current dot valid equals 1. Well, list bracket 4 dot valid equals 1. That sets that to a 1. List bracket current dot data equals n. So index 4's data should be set equal to 10. Well, those were pretty easy. Okay, previous is the index of the node after which we're inserting. What's the value of previous here?
Zero?
It's a 0. It's the sentinel node. Okay, now the sentinel is not part of our data, but it is a node in the linked list. It's this first node here, and to insert a 10, we want to insert it after this node. This is index 0. Okay, this is what the sentinel node is doing for us. It's getting rid of a special case. And when we write our code, it should simply tell us the node we're inserting after is node index 0. So previous will be equal to 0. And now if we do these 2 steps, they're just automatically going to work. Take list current dot next, that's this field right here, set it equal to list previous dot next. Previous is a 0, previous dot next is a 1. This becomes a 1. And then list previous dot next equals current. Well, list 0 dot next should be set equal to current, which is a 4. This becomes a 4. And that will be your new linked list. So sentinel points to the first node, which is a 10. That points to a 30. That points to a 35. That points to a 40. That's the end of the list. So as a nice clean picture, right, this is what our list looks like. Sentinel points to 10, to 30, to 35, to 40. But in fact, what we've done was we made a 10 up here, and we changed our sentinel to point to the 10. And we changed the 10 to point where the sentinel was pointing, which was the 30. Now when you're working on this, right, you want to draw the nice neat pictures. When you're debugging this using GDB, your pictures are going to look more like this, right, because this is what's actually going on. There's a bridge to be made between what the memory maps are going to tell you with this and what's actually the nice structure of your list. Okay, so let me make a bold statement here. All right, this code is worthless. Do not memorize this. Do not write it down on your sheet of notes for exams. Do not commit it to memory. Do not practice typing it in. This is worth nothing. Okay, the value in what's up here is the set of operations you're doing to insert a number. How do you change the elements of this array? That's the understanding you're after. And if all you take away from this is this set of 6 steps of pseudocode, you're not going to be able to work with linked lists. Because it's really hard to go from pseudocode to an understanding of how we're manipulating this structure. It's relatively straightforward if you understand how you're manipulating the structure to write pseudocode. So I want you to concentrate on understanding what are we doing to the structure, how do we insert something, how should these pointers be changed, not in terms of, list bracket current dot next equals blah blah blah, but in terms of simple arrows. If I want to insert a 25, I should put a new node here with 25. I should have the prior node point to that, and I should have the 25 point where the prior node was. That's what you want to come away from understanding. And once you understand that clearly, then it's fairly mechanical to write the code. Okay? Now it takes getting used to, and when we get to PA2 and we're doing dynamic memory, it's going to have weird syntax and stuff like that. But it's a translation process. From here's what I want the system to do to my memory, to here are the steps that I can ask it to perform. Okay? So I want you to focus not on the code itself, but on the manipulation of the underlying data structure. Okay, this is for linked lists, this is for trees, this is for heaps, this is for everything we're going to do this course. Okay, think about the data structures. Think about them visually, if visual helps you, right? And understand what's going on, and then use that to write pseudocode, and then use that to write C code. And then test your C code, and if it's not working, you can use the debugger to see what's happening to memory and compare it to what you wanted to have happen to memory. Oh, I wanted this 10 to point to my 25, but when I look at 10, it's actually pointing to null. Okay, there's a problem there. Where in my code did I tell it that my 10 should point to 25? Let's put a breakpoint right before that, and let's study what's happening. Right, so we'll get lots of practice debugging. All right, so inserting at the beginning of the list works exactly the same as inserting anywhere else because of the Sentinel node, which is why we deal with Sentinels. So here's our current list with 4 pieces of data in there. Let's do a deletion. So let's delete node 30. So think about what you have to update on your tables to delete node 30. Cool. Cool. It's pretty easy, right? Well, it's easy for us. It's never easy for the computer. But that's our job as programmers, right? Is to tell the computer what steps to perform. All right, so everybody's got this, right? To delete the 30, the main thing we have to do is take the node that comes before it and say skip over the 30. Take this previous node and say, hey, point wherever the 30 is pointing. Well, if the 30 is pointing at a 3, the previous node is index 4, that's the 10. So change 10's next field, instead of pointing to 1, point to 3. That changes this arrow to skip over the 30. And then the other thing that everybody got, which is awesome, is change the valid flag on 30 to be a 0, to say this is no longer being used. That's all there is to deletion. And if you delete the first node, the previous node will be the Sentinel. That's the pointer that you'll change to skip over the first node. Again, it's going to work exactly the same, whether you delete the first node, the last node, or a node in the middle. So we could write pseudocode for that, but before we do that, if we were to look at this in memory, we would see the following. The Sentinel points to 10, which points to 35, which points to 40. We might also notice that there's a node here with a 30 that's also pointing to 35. That's not a problem. Okay? Nothing is ever pointing to this 30 node. We changed the only thing that was pointing to it, which was 10. Nothing's pointing to it. So we might notice that if we just sort of did a memory dump, we might say, hey, here's that 30, I thought I deleted that. Well, it's still going to be in memory unless we change this 30 to some other value, but it's not a part of our list because it's not in that chain of pointers. Okay? So again, it's the concept of how these nodes link to one another that's most critical. And if we start from the Sentinel and we just follow the links, we will not bump into that 30.
But for security reasons, if we were trying to do this, that's not.
But for security reasons, when you delete a node like this, the data is still there. And if you end your process and some other process gets hold of that memory now, it can get to the data that was in the linked list. Right? So this is not a secure way to delete things. You would want to actually go ahead and overwrite that value, probably several times with alternating patterns of ones and zeros, and then you're into the DoD Orange book on security procedures. But it's a good thing to know, right? All right, so real quickly, what does the pseudocode look like for deletion? So we want to delete node N. Previous equals index of prior node. Current equals index of the node to delete. So you have to find those, and we'll talk about searching tomorrow. And then we did two things, right? We took the previous node and we set it so that it was pointing wherever the deleted node is pointing. So list bracket previous dot next equals list bracket current dot next. That's skipping the arrow over the current node. And then list bracket current dot valid equals 0. That says the node's not in use anymore. All right, making some sense? All right, so tomorrow we'll talk about PA1, we'll talk about the next ODP, but I also want to talk about something called abstract data types. And really briefly, in 55 seconds or less, an abstract data type is the idea that this particular implementation of a linked list has a lot of details. We use a -1 for the end of the list. We use an array of structures where the structure is defined to have a next, a data, and a valid in a certain order, and there are certain types of variables. We could use a character for valid. It's really just a flag, right? We could use a double for the data if we wanted to store real numbers. We could have an array where our Sentinel node is index 11. Okay, there's lots of details to how we implement this. As a user who simply wants access to a linked list, we don't care about those details. And we never want the user to have to understand our implementation of a data structure. So we're going to introduce this concept of an abstract data structure and say, what does a linked list look like to a user? What aspects of it are relevant to the person who's using it, and which ones are irrelevant? And we're going to build this really, really strong division between implementation details that we care about as the implementers of the linked list and the way that a user is going to use a linked list, which is I want to insert, I want to delete, I want to search, I want to initialize, versus I want to find an entry where the valid field is equal to 0. Okay, so the user view of a linked list, that will be what we call an abstract linked list. And so that's going to be a part of PA1, is getting this separation between how we implement versus how we use. Okay, so we'll be talking about that tomorrow also. That's abstract data types. All right, so let me put these back here and just pick one up on your way out as a worksheet. And I would like you to do what we did on the board for the following operations. So I'd like you to insert a 10 and a 20 and a 5 and a 15, and then delete a 10, insert a 2, insert a 25, and then delete a 2. So do those 4 inserts, delete a 10, do 2 more inserts, delete a 2. And bring that in tomorrow, you can put your name on it, but I'm not going to record a grade on this, okay? But I'll give you feedback on it. I just want to make sure that people are comfortable with these operations. So work probably 2 instructions per array and then copy it over so I can follow how you got from one set to the next. All right, I'll see you next time.